Howdy, folks. How's it going? Let me get my business together here. Oh, see all my notes there. Okay, so I wanted to talk in this lecture about perception. The way our eye perceives things, there's been a lot of work in the field of cognitive science, really realizing how our eye perceives things, and a lot of that work happens within the world of thinking about optical illusions. So I'd like to weigh a little heavily on some of those. What you're looking at here is a optical illusion made in 1889 by Franz Müller-Lyer. The whole idea was that by changing the direction of the arrowheads on the line, it could make the line look either longer or shorter. So what we found with a lot of these things is that by short-circuiting our perceptual system, we can learn something about how the brain perceives information and why that might be for even an evolutionary purpose or something else. So the first thing to remember is that we see in 2D, not 3D. The visual cortex turns 2D images on our retina into a 3D representation. What you're looking at here is a stereoscopic image that you would wear glasses, and then it would give the effect of being a 3D image by separating out the red and green channels in terms of how we see. There's a lot of these sort of audio stereograms and illusions, and they have to do with sort of how we see, really. The idea of stereo vision, 2D vision, 3D vision, or cyclopean vision, meaning just a one-eyed vision. So if you're seeing the effect on this particular one, it should be the effect of all of these different things moving around, kind of turning in circles. Of course, to make the illusion stop, all you have to do is pick one spot and look at it and stare at that one spot and not let your eye move from that one spot, and everything else should stop. Once you actually move around, first of all, by seeing it turning around like that, you realize how much our eye does move around. It's constantly looking over things. But you also sort of see how our brain perceives that information. Now, a lot of that's because of the way these things are structured. So a lot of our brain is sort of about how we're seeing things. This can also be about depth. Same thing in this one. If you stop and look at one point, the effect will stop, but you have to stare at an exact point and not move away from it. Once your eye wanders over the image, you start to see, it seems like a sense of shallow depth of these things getting larger. In our brains, we've also seemed to have some sort of sense for edge detection. And you know, obviously, there's a lot of really important reasons for this sort of stuff, in that we can see when something is the edge of a table as opposed to a floor, and that way we don't run into things. So this is kind of critical. This also becomes really important to just sort of navigating around to where you aren't constantly bumping into things, or thinking about in terms of the relativity of color and shadow. So for instance, in this optical illusion, it seems that the orange, let me see if I can get my cursor over here, the orange square right here seems very different from the brown square right here, but in fact they're the exact same color. And by the exact same color, I mean that if I was to cut out this image right here, and to cut out this image right here, and to put them next to one another, I would find that they actually look exactly the same. They don't look at all the same in their various contexts in different parts of the cube. But this is something that we've found about the way our eyes. So your eyes are constantly making adjustments to tell your brain about things and saying, oh, well, this is actually orange, when really its color is actually unknowable in some kind of way, whether it's in light and shadow. But that's your brain's, again, that's a sort of survival mechanism. And my theory really is that when the reason so many people cannot draw from life naturally is because it doesn't suit us from an evolutionary perspective to draw from life. To draw from life means short-circuiting your cognitive system that tells you about depth and about edges and about various kinds of things about light and dark and how to perceive colors, and you have to draw what's actually there, meaning ratios and proportions and these sorts of things. So we aren't set up to do that. Otherwise, we wouldn't be able to drive down the road. We'd constantly be fearful that the road would be kind of coming into a little point right in front of our faces. Of course, we know that's not the case because those lines going into a point is really just perspective going off into the vanishing point along the horizon line. Here's a really fascinating one too. So this is one of the most interesting optical illusions to me. Both of these images are exactly the same. It's two of exactly the same image right next to each other. The one on the right, though, feels like it's tilted. It feels like it's tilted to the right, but it's not. They're both exactly the same image. The reason that we see one of them as being tilted instead of the other is because of the way we perceive depth. So normally, if we were looking at two little towers like this that we were looking up at, we would assume that they would converge together. And that would be sort of the way that they would work, because that's the way it works with formal perspective. That's the way it works with us seeing. So since they're not doing that, our brain starts to make an adjustment to where we see one as being more tilted than the other. It's a sort of a fascinating thing. And once you actually spend a moment looking at it, then you see that this is a way that it's sort of short-circuiting how we see things. Again, same thing here. Two of the exact same images put next to each other. The one on the right feels like it's rotated further in a clockwise direction from the one on the left, even though they're the exact same image. Again, by having them right up next to each other, it plays with our sense of perspective, because these things should not be the case. So it's trying to make some sort of visual compensation about seeing these two images together. Fascinating. And just to sort of show you, here would be an image of two little girls. So you can see within this one, we don't have that effect. So it doesn't work with everything. It only works with things going off into distance. So whenever we see things that are going off into distance, then our brain makes that kind of adjustment to keep it real, to keep it to where it makes sense to our brain. When I put two images of cartoon girls next to each other like this, it doesn't happen like that. It's not a problem. So inside of our eyes, there are two things we have. We have cones and rods. We have about 7 million cones in our eyes, which are really need a high light sensitivity in our central vision. And then we have 125 million rods, so that's almost 20 times more rods than cones. And those are for low light sensitivity in our peripheral vision. So because of that, because all those rods, and there's so many of them, are good for low light sensitivity, that usually means in dark, it's better not to look directly at something, looking just to the side of it to where it's not being processed by your central vision, but rather by your peripheral vision, will help you to see it better. Now, our central vision is usually used for recognizing faces and reading text. Those are the two dominant things that we use them for. So, for instance, if I had macular degeneration and I'm driving down the road, I wouldn't be able to read the street signs very well. If somebody walked out in front of me, I would see that they were walking out in front of me through my peripheral vision, and I would stop before I hit them, but I wouldn't be able to tell that that was my friend Jerry walking in front of me. So that's sort of the difference between the cones and the rods. Usually that central vision, it's always changing. It's always whatever you're directly looking at. So you can imagine how frustrating this is for people that do have macular degeneration. A lot of times they need a lot of light on something to read it, so they have to have things really bright, because otherwise they have almost what feels like a dim gray section in the middle of their vision wherever they're looking. Also, thinking about surface, just by having these alternating, because of the way our brain works from an evolutionary perspective, we almost feel like one thing is floating over the other and sort of moving back and forth. And again, just by playing with these sort of directions of the black and white lines, again, playing with our visual cortex system to really sort of understand how it works. Now, I'm not interested in you guys going into really great detail about the sort of biology of the eye and how the eye works. But I do want you to understand these things because they do really become important as you start creating things later, especially in terms of things of thinking about people that have color blindness or macular degeneration or something like that, and really designing things for those people in mind. Again, kind of a same thing here, that you feel like the squares are moving almost in opposite directions. And again, a lot of that has to do with these lines. It's pulling them in whatever direction it's going in. So those little white and black lines on either side of the little blue squares are actually almost like an abstraction for a highlight and a shadow. And they start to tell us something about the lighting and shading, which then starts to help these things feel like they're pulling in certain directions. Or something like this. It could be really sort of difficult to unravel our visual system's hardwiring, but you can see for this, it looks like almost diagonal lines because of the offsetting of these purple bars in the vertical direction. But if you look closely, you'll see that all the horizontal lines are not diagonal. They're all absolutely parallel to the ground. But because of the way it's structured, it feels like they're pinched on one end and wider on the other, and it's a bunch of diagonal lines. And that's just simply from offsetting these things. So we see this, we see all kinds of things like this in fashion, you know, vertical lines to help people look slimmer and that sort of thing. I think I have another example of this, of a building using the same technique. And again, all of these things are running parallel, but they don't feel like they're running parallel. They feel like they're actually moving at diagonals. Or here, again, you notice how by playing with light and dark, or almost abstractions for things, you can completely change the look of something. So here you have just a normal chessboard that we're looking at, but the chessboard certainly doesn't feel normal. In fact, it feels like a bubble that we're looking at and looking on top of. But that bubble effect is really just a matter of all of these little jewel things that have been put on it, these little beads, purple and white beads, that help to make it sort of seem like it's a sort of shallow depth to it, or that it's actually stretching out parts of the image to where it's not just a clean checkers or chessboard that we're looking at. Here's an example of a color blindness test. This is really the sort of the standard, and you can see in this test what we're seeing here is certain colors that are very obvious, these brown colors compared to the green colors. It's very obvious that this is a number 6 for people with that do not have color blindness. But for people that do, since they share the same value, that's the problem, is that it just looks exactly the same color. And there's some places you can go to correct that. One that I might recommend right off the bat is vischeck.com. I think it's VISCHECK.com. Vischeck.com is a website where you can actually run images or entire websites through it, to where you can see what that image would look like to a person with certain kinds of color blindness. Of course, there's more than one kind of color blindness. So I would recommend that for your own images, just to check them. I mean, we're not talking about an insignificant number of people. I've heard as much as 9% of men and 1/2 of 1% of women. So we're talking really millions and millions and millions of people that have color blindness. And if you add on top of that people that have some form of macular degeneration, a great deal of those people older people, but some younger as well, then we're talking about a substantial percentage of the U.S. population. So it's definitely worth your while to think about those. Also, with here you see this was one done to sort of show how our brain sort of ties things together and creates these categories. So if you don't create categories, other people will create them for you. So it's good to make sure you have your categories correct. So again, here you start out with the words red, blue, orange, purple, and it starts out seeming fine enough. The red is red, the word blue is blue, etc. But then as we go down, it starts to get different. So red and orange both are the color blue. Blue is the color red. Red is the color color green. And it becomes very hard to say these things out loud. Now, in this case, it's not as dramatic of a short-circuiting of our system as the two towers we were looking at earlier, because in this case it doesn't take much, and you can override this tendency to call out the color rather than the word, and do it within a time or two of practicing. And some people are just naturally better at it than others. With the actual two towers next to each other, our brain cannot fix it. It just cannot get it back correctly. We have to look all around the edges and measure things to see that, yes, that is indeed two of the exact same pictures, but they certainly don't look like it when we look at them next to each other. And I just put this one in there for fun, you know, that idea of what we see. There's a part in our brain called the amygdala, which is kind of, I've heard it referred to as the lizard brain. So whenever you see something with your eyes, there's a very quick path straight to that amygdala, that lizard brain. That's the really hardcore stuff to keep you alive. So, for instance, when you're taking a lovely little walk in the woods, as I'd like to, as the weather gets nice around here, and you look down and you see something kind of curly, and you jump back before you even realize, thinking perhaps it's a snake. And then that's that initial information coming in, going straight to the amygdala. And that information that comes in through your eye and goes to the amygdala goes straight there. But it doesn't have a lot of information. It's only giving a little bit of information, just enough for you to know that this could be dangerous and you better get out of the way. Well, there's a slower path that gives more detailed information that goes into various other parts of the brain. And once those happen, which happen slower, then you say, oh, it's just a stick, but it looked like possibly a snake. So you see the same thing here with Chihuahua or Muffin, you know, trying to make sense of the sort of graphic similarities between the Chihuahua's faces and the blueberry muffins. Again here, thinking about, I'm really trying to underscore the difference between what is in our central vision and what is in our peripheral vision. So your central vision is whatever you're looking at within any given moment in time, and that's changing every fraction of a second. You are always sort of looking around things. If you're looking at someone, you're not just looking at their left eye. You're looking at their left eye, at their right eye, at their nose, at their eyebrows, at their earlobe. You're constantly changing your eye view. Our eyes look around and wander quite a bit. This is the whole Rubin face vase idea, which was playing off of our understanding of figure-ground relationships. So it becomes sort of a double image, right? Or if we look at the black, it's a vase. If we look at the white, it's two faces. Ironically, with this particular optical illusion, you can't ever see both at exactly the same time. You either see the vase or you see the faces. And what they found in labs with these kinds of images is that you can't ever see both at exactly the same time. Here's a great example. I think this is a little video too that sort of shows this in a little more detail. Going one way, we see the white, and then you can see that switch that happens in your brain when it starts moving the other way with the black, that all of a sudden you have a switch with the figure-ground relationship. Anyway, so that gives you a bit of an idea of it. Obviously, Escher, M.C. Escher, was sort of famous for working in this way, working with various kinds of mathematically improbable spaces, metamorphoses, and also working with these sort of figure-ground relationships and what they sort of represented. These also become important once we start getting into logo design. You know, in this case, the idea of this little arrow being sort of carved out of the E and X to really say, go, you know, Federal Express, we're here to take you somewhere, to where there's like a subtext to the image enclosed in the positive, negative, the figure-ground relationship. So this can be a really strong design choice, especially in terms of logo design. We've also found that we have a really poor ability to read and see sideways. So this here is a map of Africa turned on its side. if you look at it, it doesn't immediately look like a map of Africa because we start reading it in a different way. And I'm sure most of you have had this instance where you decide to lay in bed on your side and read a book, and you realize you can't read the book unless you turn the book to orient with your eyes. That is, you can't have a book that's parallel to the ground while your body is perpendicular to the ground, while your eyes are perpendicular to the ground. So it becomes very hard to read things like that. Here's another sort of figured ground one that a lot of people have worked with, the idea of duck and rabbit, whether we're looking at a duck or whether we're looking at a rabbit. And again, you can constantly shift back and forth between the two to try to understand the orientation of things, which we do. Now, that's not to say that this is a poor design choice. This kind of thing can be a really excellent design choice because we love solving riddles and little quizzes and problems and these sort of visual things. People get endlessly fascinated with these kind of things. So it can be a really sort of strong design choice, especially if you're really wanting to draw people in, because they'll get really sort of fascinated by how it works. We also have some visual rotation mechanism uses inside of us, so various input come to a conclusion about how to perceive the visual field. For instance, here in this one, what do we make of this cube? Is this the front side of the cube, the front angle, and this is the underside here that we're seeing and looking up into the inside of it through here? Or is it something else? Is this the front side of it, and up here it's open to where we're looking down inside of it? So you can see that, you know, sometimes we can kind of play with these figure ground relationships to various kinds of effects. We usually identify objects by recognizing patterns. We've got all kinds of patterns that we sort of put into our minds from childhood onward. And you could see right here, I know this is just an abstraction, but sort of thinking about things generally, we would think of this as 8 dots. Probably more people would say this is 4 sets of 2 dots if pressed on the issue. So by their proximity to one another, we see them as being grouped together. And this can become really important when you're getting into all kinds of other things. Similarly here, oops, sorry for the resolution here. I should have done a higher scan of this. These patterns help us to define what we're seeing. You know, so if we looked at the objects on the top of this image, we'd probably say they're triangles. But if we looked at the images that are more in this area, we would probably say that they're squares turned to their side, and that's because of their pattern together, that they feel like squares that are all moving in a downward diagonal direction, whereas up here it feels like triangles that are all together. So again, these are the very basics of the Gestalt theories of perception that we're going to get into when we get into information design. They become sort of critical to understanding how to design things in such a way to where people put the right things together that they're supposed to put together. Again, here, if I asked you which direction these triangles were pointed, ironically, and you probably saw some of these in Steven Pinker's book, the triangles on the left most people would say are pointed to the right, and the triangles on the right most people say would be pointed to the downward right. So we all have a sort of way that we, by the orientation of things and by the things surrounding it, that's what helps us sort of orient how they work. Or again, enclosing things to give us a sort of feel for it. Stop war, peace now, or stop peace, war now. So these are things that are really easy to use in design thinking. Kind of some of these optical ideas and thinking about the way we parse information in our eyes that can really help with design. You can see here's one of those things. We see this image, and we see right next to it hundreds stranded as snow closes key routes to LA. And it kind of, you think maybe that's what you're seeing here, but in fact, this image actually goes down here with this one. Brown's first 100 days could be critical. So this image right here is actually somebody getting ready for an inauguration, above preparations for today's inauguration. But because of the proximity effect, it's not clear what this goes with, if it goes with this image or this one. Again, here our brain creates shortcuts and fills in the blanks. What we found is that when we read, we don't read individual letters. We actually take in groups of letters at a time. Now, I would take issue with this, that only smart people can read this. And in fact, I would argue that anyone could read this. And in fact, not only could anyone that knows how to read be able to read this, but they would be able to read it quicker and quicker, to where by the time they got to the final paragraph, they would be reading almost as fast as they would if all of the letters were oriented correctly. So we know that we're not taking in everything as individual pieces, but taking in the shapes of the words as a whole, and that's sort of how we put them together. So, and I think just reading this, you can sort of see how the brain works to fill in the blanks. Now, that filling in the blanks becomes really important in certain situations, but before I get to that, here's one more. There are some things that our brains aren't so well wired for to perform so well. For instance, if I asked you how many letter F's are in this particular line of text, most people would say that there are 5 F's in here. There are actually 6 F's in this line of text. And the thing that they found is that most people forget this one. I suppose they're counting pretty well up through the top, and then perhaps because of the alignment of the 2 ofs, or perhaps because once they get to the second line there are no F's, that they just skip right over it. And perhaps that's also a bit of competitiveness, that everyone's trying to be first to decide how many F's are in it. Here is the Knieza triangle. So the Knieza triangle really shows how our brain can sort of fill in those blanks that I was talking about. So you can see that there's no triangle here. In terms of the white triangle, the white triangle is completely constructed out of an implied space, just by having these little Pac-Man type figures oriented with some cuts in this black triangle. It creates a white triangle, but look at how strong that white triangle is. You would almost feel like there's a line around it to where it's crystal clear. Even in the points where there's nothing there, you see a line there. Our brain continues it right on along. So this can be a really helpful tool in understanding this to design things. What we have to have, what we don't have to have, and what we can actually subtract and make more interesting. Here's another version of that, the Knieza rectangle. And again, you can see even at this point, there's even nothing else in the background. It's just the little Pac-Man type characters. And again, the rectangle still holds up relatively well with just such a little bit of information playing on it. There is another theory about how we see things that's related to what's called geons. And the geon theory, and this is actually not as settled of science, I don't think. But the geon theory is that in our brain we have a number of sort of primitive shapes that we read things as. For instance, like here you see a cylinder that's pinched on one end, you know, a cubic form that's pinched on one end, a sort of long, stretched, and perhaps bent cylinder. And then you can see how they begin to use those over here to put them together to make objects, right? And there is this kind of idea that because of these various geons in our brain's understanding of them, that becomes to make these objects and the way we read objects. Now, whether that plays out in further studies in cognitive science or not is another question. But this is certainly useful in iconography and drawing, cartooning, this stuff, because we immediately recognize all of these objects in terms of how they're put together. They're symbols. They don't look real at all. This doesn't look like a coffee cup, but everyone would say coffee cup to this, or perhaps teacup. No one would say this is a water bottle. No one would say that this is a pitcher or something like that. So you can see with very little information visually, you can get across a lot of ideas in simple ways. What you're looking at here is a coffee cup, and this is what we would call the canonical perspective. What we found is that if we asked people to imagine objects they imagine them tilted and at an angle slightly above, as if that object that we're asking them to imagine is sitting on the table in front of them, and they're looking down at it. So, for instance, the scientist that did the study, Stephen Palmer, I believe at the University of Saskatchewan, asked a number of people to draw their idea of a coffee cup. And this is what he got. And you can see here, this says a lot about right-handed people too, doesn't it? All these, I'm sure all these people right-handed because they have the handle on the right side. I'd be interested to know if a left-handed person would put the handle on the left side. But all of these very, very similar. Maybe in some cases, like here, you see it's a little bit lower for perspective, but still an upper perspective where you can see into the cup. And then some of these that are much higher perspective, but still variations on the same thing. What you don't see when you ask somebody to think of a coffee cup is something like this. So, I should also mention that we have a special part of the brain for recognizing faces. Once you get into the idea of faces, as you can see with this image, it doesn't take much, and you can get a great deal of information. And a lot of very personalized information, just very little things. I mean, you're talking about such a small area, you know, perhaps as little as 9 or 10 square inches. But through that, we learn all kinds of really intricate things about someone and can take a read on someone, not just their mood, but their intentions, all that sort of thing. And people can be quite accurate about that sort of thing. And then also thinking about faces, we tend to look at what other people are looking at. So if people are looking at something, we look at it too. Marketers use this all the time. You see people looking at things in ad. If you want them to look at something, you have someone else look at it. I'm sure there's an evolutionary reason for this. My assumption would be it would have to do with, again, with survival. If a lot of people were looking at something, it could be that there was something dangerous that I needed to know at and look at as well. So this is something that is always kind of worth keeping in the back of your head. And also, we decide what is alive by looking at the eyes. So when we look at the eyes, and this doesn't just play out for humans, but any kind of animal, that's how we decide what is actually alive and what's not. So you can see here, what point does this character in this image go from being a photograph of a human and actually become a artificial drawing? And most people would say it's somewhere in this area. And that has a lot to do with the eyes. I mean, by the time we get to here, it feels very artificial. So, anyway, I just wanted to give you that. That's a little taste. Do your assignments, and I'll see you on the discussion board.